Okay, for the last video in section 11.1, we're going to look at question 9. And part A says, find an equation for the tangent line of the curve, x equals secant squared of t minus 1, and y equals tangent of t at the point when t is equal to negative pi over 4. And so to begin, let's go ahead and find the slope of the tangent line to this curve at the point when t equals negative pi over 4. And so to begin, we'll compute dy dx. And to compute this in terms of the parameter t, we find dy dt and then divide that by dx dt. And for dy dt, I want to differentiate tangent of t, and that's secant squared of t. And then for dx dt, I want to differentiate secant squared of t. Now, got to apply the power rule along with the chain rule. So power rule says bring this 2 down, and that'll give us a 2 secant of t. And then the chain rule says to multiply this by the derivative of what's inside the square. So in other words, multiply by the derivative of secant of t. And that is secant t times tangent of t. And now notice that there's a secant squared of t in the numerator, and then I have a secant times a secant here, so that's secant squared of t as well. And so simplify, and I can divide out the secant squared of t, leaving with the result that dy dx is 1 over 2 times the tangent of t. And so in particular, dy dx, when t is negative pi over 4, is 1 over 2 times the tangent of negative pi over 4. And the tangent of negative pi over 4 is negative 1, and so this is equal to negative 1/2. Okay. So this value we just found, negative 1/2, is the slope of the tangent at the point when t is equal to negative pi over 4. And to find the coordinates of that corresponding point, I can find that by plugging in t equals negative pi over 4 in these equations for x and y. So note that x is the secant squared of negative pi over 4 minus 1. And this simplifies to 1. Why? Well, what's the secant of negative pi over 4? It's the reciprocal of the cosine of negative pi over 4. Cosine of negative pi over 4 is the square root of 2 over 2. So its reciprocal is 2 over the square root of 2, which simplifies to the square root of 2. We're then squaring that, and that's going to give us a 2. And then 2 take away 1 gives us the 1. For the y-coordinate, we have tangent to negative pi over 4, and that is negative 1. All right, so putting this all together, the tangent line at 1, negative 1 can be found using point-slope form. So I have y minus the y-coordinate of our point, so that's y minus negative 1, so I have a y plus 1 on the left side, and that's equal to the slope, negative 1/2, times the quantity x minus the x-coordinate of our given point, and that's 1. And then rearranging, y is equal to negative 1/2 x minus 1/2. All right, and that does it. Part B, it says find the rectangular equation for this curve by eliminating the parameter and sketch its graph, including the tangent line you found in part A. All right, now notice I have a secant squared of t in the equation for x and a tangent of t in the equation for y. Okay, so I want to think back to pre-calculus, in particular to identities, and this identity, which is a variant of the Pythagorean identity, is particularly useful. Okay, it says that the tangent squared of t plus 1 is equal to the secant squared of t. Okay, and where did this come from? It just comes from the standard Pythagorean identity, sine squared of t plus cosine squared of t is equal to 1. If I divide both sides of this equation by cosine squared of t, on the left side I'll get sine squared of t over cosine squared of t, well that's tangent squared of t, plus cosine squared of t divided by itself, well that's 1, and that's equal to 1 over cosine squared of t, well that's secant squared of t. All right, so why is this useful here? Well, first note that I can rewrite this equation if I subtract 1 from both sides, and I have that tangent squared of t is equal to secant squared of t minus 1. And see, what's tangent squared of t in terms of x and y? Well, y is tangent of t, and so tangent squared of t is just y squared. What about the right-hand side? Secant squared of t minus 1? Well, that's just the x-coordinate. So, in turn, I conclude that y squared is equal to x. This is a rectangular equation for the curve described by these parametric equations. All right, so go ahead and sketch that curve. It's this parabola opening to the right and passes through the origin. Okay, and now as I let the parameter t increase, how do I move along this blue curve? Well, first, looking back at the component functions, so my equation for x and my equation for y. Well, y is the tangent of t, and this is a relatively familiar graph from pre-calculus. So it has vertical asymptotes at negative pi over 2 and pi over 2, and this is an increasing function. Okay, so this tells me that as I increase the parameter t, y is increasing, meaning I'm moving upwards, okay, as I trace this curve. What about the x-coordinate? It's a little more complicated, but the secant has vertical asymptotes at negative pi over 2 and pi over 2. And notice when t is 0, I get that the secant squared of 0, which is, well, 1 squared, because secant of 0 is 1. So 1 squared minus 1 is 0. So the x-coordinate when t is 0 is 0. So we pass through the origin here, and then I have these vertical asymptotes. Okay, so what that's telling me is that as I let t increase from minus pi over 2 to pi over 2, x is going to come from positive infinity, it's decreasing to 0, and then it's going to shoot back out to positive infinity. Okay, so it's going to come from out here, it's going to come in, hit the origin, and then go back out. Okay, so if you put those motions together, right, y is increasing, so we're moving up, and x comes in, touches the origin, and goes back out. If you put those two together, okay, this implies that our tracing particle is going to move in the direction indicated by these arrows. Okay, and then for our tangent line, well, that was at the point 1, negative 1, which is on this lower branch of the parabola, and there's the tangent line there in green. All right, so now let's check that out on the graph. Just put the parametric equations in here. Here's our tracing point. There's the point 1, negative 1, and the equation of the tangent line. Yep, looks pretty darn tangent to me. And let's check out this tracing point. So we let t vary from minus pi over 2 to pi over 2. You can see it comes in from way out here, right? And then it slows down a lot, and then it whips back out. And there you go. Cool. Well, that's going to do it for this video as well as for the section. And I'll see you next time in section 11.2 on polar curves. All right, thanks so much.